All right, so good evening and welcome to this Mathematics 1 class. We'll continue our example session and example session from yesterday. Again, there's a lot of requests for exam problems. I picked out a couple that hopefully will get done today. So let's start right away with the first problem here. This is from 2019, exam 2, problem 3 of an orthonormal basis. So let's take a couple minutes and see if you can get the right result. Quick remark, there's again a question on TweetBack. I'm only asking for the dimension of u because it's not very nice to write those vectors in TweetBack. So just use that as an indication when you're done. usual question, who of you is done already? Who wants some more time? Let's give it 2 more minutes then. And I trust the rest has already done this at home. Right, so here's your results. Most of you said dimension of u is 2, and of course that is correct. The dimension of u is 2. Now let's take a quick look at how to answer that question. Before we do that, let me point out that actually the question is also asking for the dimension of u explicitly. If that is part of the question, please don't forget to answer it. Many people just forgot that and missed, I think, 2 points. Totally unnecessary. All right, so determine an orthogonal basis of R3 such that the first dim u vectors of that basis form a basis of u. Now, what is that problem asking us to do? Basically, that's a convoluted way of saying I want an O and B of u, and I want then to extend that O and B of u such that I get an O and B of R3, right? How do I do that? Well, u covers part of R3, and to cover the rest, I need to have a basis of the orthogonal space to u. So what I also want is an O and B of u orthogonal. Put those two together, and we have a basis for the whole space. That is also an O and B. Right, so I could also have asked, determine an O and B of u and an O and B of u ortho. Same thing. All right, now my intention with this problem was the following easy solution. If you look at those two vectors closely enough, you can hopefully see that a scalar product is 0. Right? 1 plus 1 minus 2, that's 0. So those two vectors are orthogonal already. That means for an O and B of u, it's sufficient to just normalize those two. Right? That's all. And then to get an O and B of R3, take those two, add a vector that is orthogonal to both of them. How you get that? doesn't really matter. In this case, it's easy to guess one. And then normalize this if necessary, and you're done. Right, so that would have been the easy approach. Just state that the scalar product of those two vectors is 1 plus 1 minus 2, that is 0. So those are orthogonal. And that means I can easily get the desired orthonormal basis of U by just normalizing. To normalize the first one, I divide that by square root of 3. And for the second one, it would be the square root of 1, 2, 4 of 6. So this is an ONB of U. And then let's just guess the third one. I mean, if you look at those closely, you see they both have a 1, 1 here. So, for example, we could take a vector like 1, minus 1, 0. The scalar product of that one with this is 0, and the scalar product of that vector with this is also 0. So it's orthogonal to both of them. So this is orthogonal to U. So that means if I add that, I'll have a basis of R3. And again, to get an ONB, I just normalize it. And to normalize that, I divide by square root of 2. So this is an ONB of R3 that also has the desired properties. Right, so that was the idea. Surprisingly, very few people got that. Question? The question asks for an orthonormal basis of R3, so yes, such that the first dim U is 2, vectors of the basis form a basis of U. Yeah, I mean, if you have that basis here, this one, then obviously you can also state that the dimension of U at this point is 2. Orthogonal vectors are always linearly independent, so we know the dimension right away. Yes? So if the implication is obvious, like here, for example, you write down a basis and then you say something like this implies the dimension is 2. Right? If the basis has 2 elements, I'd say that's obvious enough. Yes? Sorry, 1 over which square root? This normalization step here. So what I'm doing is I'm computing the norm of this vector. The norm is the square root of the sum of squares of the entries, right? So this is 1, let me write that down. The norm of 1, 1, 1 is the square root of 1 squared plus 1 squared plus 1 squared, right? So that's square root of 3. And I'm dividing by that norm to normalize the vector so that the resulting vector has a length of 1. Okay? Same thing for the others. Yes? Mm-hmm. Mm-hmm. Yeah, let me get to that. So, of course, what you also could do is let's say you fail to see that those are orthogonal. Let's say you fail to guess that third vector. Of course, there is an alternative way of solving that. It's just a little more work. So let me maybe present that as well. So the alternative is to just apply the standard recipe in a way. You take these vectors and you perform Gram-Schmidt's method on them. Right, so what you do is you do Gram-Schmidt. First step is the same. You normalize the first vector, 1, 1, minus 1, divided by the square root of 3. For the second step, let's say you don't see that those are already orthogonal. Of course, you could still do Gram-Schmidt's method. Doesn't really make a difference. So what you would do then is you take that second vector, 1, 1, 2, 1, 1, 2, and you subtract its projection onto the first vector. So the projection onto the first vector, you get that by computing the scalar product with that first vector times the first vector. And remember to use the normalized vector for this projection, otherwise the values might not be correct. Right, so what happens then is you get 1, 1, 2 minus, and I already said the scalar product is going to be 0. Right, so what you get is just this original vector. Just what you would expect happens if you know those are orthogonal, but Gram-Schmidt will tell you so, even if you don't recognize that. And then, of course, you normalize. Right, so let's say this is 1 over the square root of 6, 1, 1, 2. And then for the third step, let's say you don't guess that vector. And of course, you can compute it. What you can do is just add one of the unit vectors. Try that as an extension for your basis, and then orthonormalize the result. Either you'll get a vector that is orthogonal to the other two, and you're done, or you get the 0 vector. That happens if that vector that you added happened to already be in the span of the two that you have. So if the set is linearly dependent, you get a 0 vector. In that case, just continue with the next unit vector. One of those will work. Right? So for example, what I could try is I could try to add the first unit vector, 1, 0, 0, as you suggested. And then I apply Gram-Schmidt to that vector. So what I will get here, let's first do the first one, is the scalar product of that and 1, 1, minus 1. I've already taken out these two factors here to get 1 over 3. And then, of course, I do the same thing with this vector here. Again, projection. I'll take out the 1 over square root of 6 2 times. And I have the scalar product of that and 1, 1, 2. Oh, sorry, I forgot to add that vector here. Yeah. 1, 1, minus 1, minus that. And here I need to add 1, 1, 2. Okay, you just do those computations. And if you do that, you should get, let's see, that should be 1 over 2, 1 minus 1, 0. Right, so you get the exact same result that I got by just guessing, apart from that 1 over 2, but that is going to be factored out anyway. And then you normalize, and if you normalize, you'll again get 1 over the square root of 2, 1 minus 1, 0. And that yields the same O and B that we got before. You just need to put in a little more work, but you need to put in a little less thinking, so that might also be good. All right, questions about that one? Just one quick remark. Someone in Tweetback, oops, so many questions. Someone in Tweetback said, I solved this question a few hours ago and it confused me. How can an orthonormal basis consist of two vectors which have a scalar product of 0? Doesn't that mean that both vectors contain basically the same information for the projection? Two parts to answer that. First, an orthonormal basis is basically defined by saying all the vectors in that basis have a scalar product of 0 pairwise. That means they are orthogonal by definition, right? We define orthogonal through saying the scalar product is 0. So that's the definition of an orthonormal basis. And what that means is exactly the opposite. What that means is I have two vectors that point in completely opposite directions. They don't have anything in common, right? I have vectors like this that are pointing somewhat in the same direction, so there is some common aspect to those directions, right? If I have something pointing in that direction, somewhere in the middle here of those two vectors, I could capture part of that information with this vector, and I could capture part of the information with this vector, right? And it, basically, they double this information a little bit. If I have these two vectors, they're pointing in completely opposite directions of my space. So the idea of orthogonality is to kind of have complete different directions, decompose space into directions that are orthogonal to each other, so that it's easy to figure out which part of any vector I need to build with this and which part I need to build with this direction. Okay, so the idea is to avoid this duplication of information in a way. All right. Is it possible to use all three unit vectors? Just scan through those briefly. What does obtaining the 0 vector from Gram-Schmidt indicate? So if you do Gram-Schmidt, you obtain the 0 vector in that step. That means the vector that you have added is already contained in the subspace that is spanned by all the prior vectors. So that set that you get by taking those prior vectors and adding another vector is linearly dependent. Right? That means this vector doesn't add any independent new information, so the orthogonal part is 0. That's what it means. Why do we need 3 vectors for the O and B? Because the question asks for a basis of R3, and that needs 3 vectors. Are we allowed to use cross product of vectors in the exam? Yes, you are. So of course that could also have been a possible answer, and many people did that. Once you have those first 2 vectors, you can of course compute the cross product in case you know what that is. In case you don't know, trust me, you don't want to. Keep in mind this only works in 3-dimensional space, only in R3, no other dimension. Right? So if the vectors happen to be in R2 or in R4 or in R75, don't do that. Okay. Let's get to the next question. I can have a look at the others. Another exam problem that you requested. 2022, problem 4, something completely different. Consider the following points. Here's a table of points, x-coordinate, y-coordinate, and a number, k. We want an affine linear function of this form here, alpha plus beta x, with these 2 parameters that we want to determine now. And we want to determine values for these parameters such that this here, the sum of least squares errors, is minimized. Right? If you remember, hopefully, remember that we did something like this, right? You have 3 points. They're not all on a line, and basically you're looking for a line that approximates those 3 points. And you get something like this, right? So this is our function f. Okay, and we've learned a method for computing that function, which you hopefully remember. So this is your chance to practice that. Again, I'll give you a few minutes, see what you get. And I have 2 tweetback questions asking for the values of those 2 parameters here. Oops. All right, let's quickly see how we're doing. Who of you is done with the problem? Just 1, 2. Who has given up already? That's a lot more. Okay. Who still wants a couple minutes to try? Good. Give you a couple more minutes then. All right, so I'll give you 30 more seconds to submit your votes, and then we'll take a look at how to do that. We finally have a couple of right answers. All right, so here's alpha. You're pretty undecided on that one. Interesting, there's more votes for beta. Beta is here. But again, you're pretty undecided on that as well. So let's take a look at how we do that. Least squares method. You remember the idea, hopefully. The idea was to determine these values of alpha and beta such that ideally those equations here would be fulfilled for all the k's. And if that's not possible, at least minimize this error here. Okay, so the first thing you need to do is express that in matrix vector form. Or in other words, in the form of a system of linear equations that you can then either solve or approximate in a certain sense. To do that, what we want is we want to compute these f values here. So f of x1 is minus 2, is 5, f of 1 is 3, and f of 2 is minus 2 if we get an exact solution, which we won't, yeah? But that would be the ideal case. Right? Now we can express that f of something in matrix vector form. Remember, f of x is defined to be alpha plus beta x. So you can do something like express that, as a matrix times a vector alpha beta. Right? That alpha is independent of x, so it doesn't really matter which x you're using. So you always have 1 here. Right? And the beta x part, well, depends on the x. So for the first x, you get minus 2. Right? For the second, you get 1. For the third, you get 2. So basically what that is the first row here is f of minus 2. The second row is f of 1. And the third row is f of 2. Maybe better write an arrow here, not an equality sign. Okay, so you can express what you want as a system of linear equations in this way. You want to determine values for alpha and beta such that ideally this holds, and the right-hand side is going to be the y values. And the question is this solvable? Is this a feasible system? Well, the problem already suggests it might not be, and of course it is not. So what you do is you compute a least square solution. And we have covered a method for doing this. Let's call this matrix here A. And let's call this vector here B. Then what we want to do is compute the least squares solution. And you know a formula for doing that, or you should know a formula for doing that. Simply says solve the system that results from computing A transposed A times x hat equals A transposed B. And this x hat is going to be our alpha beta. Right? That gives you the least square solution. So all we need to do is compute A transpose A, compute A transpose B, and then solve a system of linear equations. Computing A transpose A, well, transposing that gives you this matrix here, 1, 1, 1, minus 2, 1, 2. And if you do the computations, I'm going to make this quick, you get this matrix, 3, 1, 1, 9. And A transpose B, 1, 1, 1, minus 2, 1, 2 times this B vector. This is 5, 3, minus 2. Again, let's make this quick. You get 6 minus 11. So what you need to do is you just need to solve this linear equation system. And those two variables here are alpha and beta. So we'll solve this for alpha and beta. I trust you all know how to solve a system of linear equations, so I'm not going to do that. What you get if you do that is beta is 3 over 2, alpha is 5 over 2. So the function that you're looking for has the form 5 over 2 minus 3 over 2x. All right? Some of you at least got one of those values correct. Of course, I'm not sure whether you got both of those values or if that were independent people. Okay, but that is how you solve it. So basically, it all amounts to first getting this formulation right, and then simply applying this formula. That's all there is to this problem. Yes, question? Could I explain the first part again? So up to this point here? All right, so again, what you're trying to do is, you're trying to find this function, determine parameters alpha and beta, such that ideally this would hold. Right? This would be possible if all of those points are on one line, right? If you have a situation like this, where all the points are actually on one line, then it will be possible to find those alpha beta parameters exactly. Okay, to do that, I'll reformulate that such that I can solve a system of linear equations. Basically, what I'm doing is, I'm substituting those points into my equation. So again, f has the form alpha plus beta x. So if I substitute my minus 2 in here, I get, well, f of minus 2 is alpha minus 2x. No, sorry, alpha minus 2 beta is 5. From this row, I will get alpha plus beta is 3. And from this row, I will get alpha plus 2 beta is minus 2, right? Just substitute those values here for x, and that's my y values, the right-hand side. Okay, so this here, this is a system of linear equations in alpha and beta. So I can write that in matrix vector form. And now I can try to solve it, and if I do, you will find it doesn't have a solution. And that's because those points are actually not on a line, so the situation is more like these orange points. There is no common line for all three of those. All right, and that's how I got to this point. And once you're there and you realize you can't solve a system, that's when you do this least squares method. And as I said, we learned through projections basically that this is the same thing as solving this system here. So what you're doing in a way geometrically is you're changing the right-hand side so that it actually has a solution, and you're trying to do so in a way that gives you the least possible error. And if you do that, this amounts to that formula here. All right, any more questions on that one? Let's take a quick look at TweetBack. Do you have any encouraging words? I'll try to bring some on Thursday. Before I say something stupid, I'd like to think about that for a minute. Maybe let's just go on with a couple more questions, and I'll prepare a pep talk for Thursday. 2019-2. Let's do some calculus. Which of the following series converge? Determine the limit if applicable. Give a justification for your answers. So 2 questions. Part A. I think most questions evolved around part B, but let's still have a quick look at A. Again, see if you can find the solutions to those. I think I have sent up a couple of tweetbacks already. Yes, I have 2 tweetback quizzes on A and B. right, as usual, a quick show of hands. Who's done with both problems already? Who still needs a couple more minutes? Let's add 2 minutes or so. Okay, I'll give you 30 more seconds to submit your votes. All right, here's the result for A. Most of you say that series does converge and the limit is 9, and of course you're right. Let's still see how to do this. You might already suspect this is going to be a geometric series. And of course your suspicion is right. You just have to reformulate it correctly. So what do you do here? Basically what we use is an expression like 2 to the 3n. That's the same thing as 2 to the 3 to the n. Right? So we can easily simplify that a little. 2 to the 3 is 8, so that's 8 to the n, and 3 squared is 9, so that's 9 to the n. Right, so what we actually have here is a complex way of writing this series 8 over 9 to the n. The geometric series converges. You remember the formula for that? Sum over q to the n from 0 to infinity is 1 over 1 minus q. If q is less than 1 in absolute values, and that is the case here, right? 8 over 9 is less than 1. So you can just apply that formula, and you get this is 1 over 1 minus 8 over 9, or 1 over 1/9, or 9. So the series does converge, and the limit is 9. Okay, any questions about this first one? Otherwise, let's take a look at the second one. And here, thankfully, a majority says the series does not converge. And that is, of course, the right answer. Let's write that down once again. So here, 4n plus 1 over n plus 2 squared from 2 to infinity. Now what we have here, basically, there's a power of n to the 1 in the numerator, a power of n squared in the denominator. So this is something like 1 over n, right? Very roughly. Of course, we need to make this more precise, but it should get across the right idea. So this is pretty similar to the harmonic series. We just need to prove it. And the idea for doing that is proving that this is larger or equal to the harmonic series, so it will diverge. That's what we're going to do. So what we have to do is we have to take this expression 4n plus 1 over n plus 2 squared. And we have to somehow compare that to 1 over n, hopefully prove that this is greater or equal to 1 over n, or something very similar. And this can be done. Let me rewrite that slightly. This can be done. Basically, I need to get rid of this numerator here, right? I'd like to replace that by 1. And I can either try to do a reformulation, or I can try to bound it, right? For the harmonic series, it would be sufficient to prove that this is greater or equal to something like 1 over n, basically. Not quite what we will be doing, but almost. And for that, I said already we'll get rid of that one. So if we want to prove that this is greater or equal to something, we can either reduce this expression in the numerator, or we can increase the expression in the denominator. In both cases, the fraction will be smaller. If we just replace one of those n over n plus 2's, one of those expressions here, by 4n plus 1, and leave the other one in place, then what happens? Well, we're starting at 2, remember? And of course, 4n plus 1 is greater or equal to n plus 2. Greater, in fact, for all n's that are greater or equal to 2. Right, so this is true as 4n plus 1 is greater or equal to n plus 2. And then we can simplify that, and we get 1 over n plus 2. And this is pretty much what we want. Right, almost 1 over n, just a little shift, right? But that doesn't really make a difference. So what we get is this series here, 4n plus 1 over n plus 2 squared from 2 to infinity, that's greater or equal to the series over 1 over n plus 2 from 2 to infinity. Okay, and that is almost the same as the harmonic series. Remember, it looks like this here, from 1 to infinity, 1 over n. There's just a little difference in a couple of summands here, right? So here we start with n equals 2, so we start with 1 over 4, then we have 1 over 5, 1 over 6, 1 over 7, and so on. So basically this starts from 1 over 4, this starts from 1 over 1. So if we want that to be the same, we subtract 1 over 1, we subtract 1 over 2, we subtract 1 over 3. Right? The 1 over 4, over 5, over 6, and so on, we just leave those because that's the ones that are also contained in this first sum here. And now we know with this here, that's a finite value, but this here diverges to infinity. Yeah, so if I have infinity and I subtract some small finite value, it's still infinity, and that means that series also diverges. Okay, so that's how you would prove that. And I agree this proof is somewhat hard to get right, but I hope you all got the general idea that this is probably a harmonic series to at least get you into the right direction. Right, questions about that one? Otherwise, we'll go on with a couple of, yep. I didn't try to apply the ratio test, did you? Does it give you anything useful? What is the result? So let's give it a try. Okay, let's see, try ratio test. So what do we have here? 4n plus 1. So our an is 4n plus 1 over n plus 2 squared. So for the ratio test, we need to compute an plus 1 over an, right? absolute value to be precise, but it's all positive here anyway, so that doesn't matter much. So what we get is 4n plus 1 plus 1, n plus 1 plus 2 squared times n plus 2 squared 4n plus 1, right? So let's see. This means we have n and n squared here, and we have n squared and n here. That looks promising. Well, yeah. So we divide by n over 3, right? And then we get, let's see, 4. No. Let's first reformulate that. 4n plus 1 plus 1, so we have 4n plus 4 plus 1. This is 5 times n plus 2 squared. I'll just write this all in one fraction to make it a little nicer. And here we have n plus 3 squared times 4n plus 1. And now let's do the division. So we get 4 plus 5 over n times 1 plus 2 over n squared. And then 1 plus 3 over n squared times 4 plus 1 over n. And that means, if I'm not mistaken, this tends to 4 and this tends to 4. So this tends to 1. Did I make a mistake? Get the same result? You all agree with what I get here? No one got a different result. Okay, so this tends to 1, and that means the ratio test is inconclusive. So unless I made a mistake here, the ratio test doesn't help. Doesn't give you any useful information. All right, any other questions? Otherwise, my next problem would be, again on serious, 2019-17. So we just continue with that same topic here. Again, give it a try, and then we look at the solution together. And again, there is a tweetback question for both A and B. usual question, who's done with part A already? Who's done with part B? Who needs more time? All right, well, let's maybe give you 30 more seconds to submit your vote, and then we'll discuss the answer to those two questions. All right, so here's your answer for part A. The series converges. An overwhelming majority said that, so it must be true. Just a quick remark here, you will see that the problem statement explicitly says you do not need to determine the respective limits. And that means the intended way is probably applying one of those convergence tests, right? Root test, ratio test, Leibniz test, you remember those? In this case, part A, you can either apply the root test or the ratio test, both will work. Maybe try the root test here first. Root test means what you do is you compute the nth root of an. In this case, an is the term inside of the sum, so an is n to the third over 3 to the power of n. Right, if you compute the nth root of that, you get 1 over 3 times the nth root of n to the power of 3. And this nth root of some polynomial in n, this converges to 1. So as n tends to infinity, this whole thing tends to 1/3 times 1. This is strictly less than 1, so that means the series converges. Right? And as I said, the root test, the ratio test will also work in this case, so it doesn't matter which one you use. Part B, this here, so with expressions of that type, I'd usually use or try to use the ratio test first because these factorial expressions, those simplify quite a lot usually if you put if you have the ratio of those. So we try with an equals n to the power of n over n factorial. We try to apply the ratio test. Quick remark, in questions like this, at least if I'm asking for a justification, don't forget to write down what you're trying to do. So something like mentioning the test that you're trying to apply might already help get you a point, even if all the rest is completely wrong. Okay, so if you do this, we need to compute an plus 1 over an. Again, it might help writing this down to show that you know what the ratio test actually is. So an plus 1 is n plus 1 to the power of n plus 1 over n plus 1 factorial times 1 over an, that is n factorial over n to the power of n. So simplifying this just a little, what we get is this n plus 1 factorial and n factorial. Those cancel out, so we're left with 1 over n plus 1 here. Right, that's nice. Then we have this n plus 1 to the power of n plus 1 and n to the power of n. Those seem pretty similar. Let's try to split off one of these n plus 1s that we will then be able to cancel out with this rest here of the factorial. So we're left with with n plus 1 to the power of n and with n to the power of n. Okay, those two cancel. And the rest, we just rewrite that slightly as n plus 1 over n to the power of n. And now you can hopefully see what's happening here. This is the same as 1 plus 1 over n to the power of n. And you remember the limit of this expression, right? This, as n tends to infinity, this tends to e. E is, of course, greater than 1, and that means by the ratio test, this series is divergent. All right, so if you have something of the form n plus 1 over n and both to some powers of n, you should always be on the lookout for something like that. Yeah. Sorry? Just with Euler series, so just let me write that down again. What you want to do is something like, compare this to the Euler series, which is this here, right? 0 to infinity. You remember this is convergent and converges to e to the power of x, right? And I'm guessing what you want to do is something like this converges to e to the n? It doesn't. No, problem here is this x, this here, that is some constant value that doesn't change with n, right? It's independent of n. This is not independent of n, so you can't do that. Right? If you take the limit, all the n's have to go away. So don't. All right, any other questions about this one? Yes. I'll get rid of what, sorry? The factorial? Okay, the factorial, easy. So here I have n plus 1 factorial, here I have n factorial. Yeah, and you remember n, oops, that's a little more than I wanted. N plus 1 factorial, that's the same thing as n factorial times n plus 1. So the n factorial part, those just cancel out, and I'm left with n plus 1. That's this one here. And this other one comes from that by just splitting off the plus 1. All right? Good. I say that should be sufficient for today. We'll have one more lesson on Thursday, and of course there'll also be exercise classes on Thursday, so there should be plenty of time to hopefully answer all of your questions then. I'll see you on Thursday.